Hello everyone, I'm Kim Hee Lee and I'm an assistant professor at the National University of Singapore. Welcome to my talk on semi-supervised learning for 3D object detection. And in today's talk, I'm going to talk about two of our works on semi-supervised 3D object detection. The first work published at ICCV 19 is on cross-category semi-supervised learning for 3D object detection on RGB-D data. And the second work published at CVPR 2020 is on in-category semi-supervised learning for 3D object detection on 3D point clouds. So we all know that the image-based 2D and 3D object detection tasks have always been popular and important in computer vision. Given an image of the scene that contains object of interest, for example, cars in this image here, the goal of object detection is to find the tightest bounding box around each object of interest in the scene and to correctly assign the object class label to each of these bounding boxes. In 2D object detection, the bounding box is parameterized by the object center, denoted as X and Y, and the bounding box width and height, denoted as W and H respectively. In 3D object detection, the bounding box is parameterized by the object center, denoted as X, Y, and Z, and the bounding box width, height, and length denoted as W, H, and L respectively. There's also an additional yaw angle denoted as theta to denote the orientation of the bounding box around the upright axis. And in the recent years, there has been a growing interest in 3D object detection with RGBD data with the easy access to RGBD sensors. In addition to the RGB image, we now also have the corresponding 3D point clouds as inputs. Similar to image-based 3D object detection, we use the 7 parameters to parameterize the 3D bounding boxes in RGBD 3D object detection. The Froston point nets was the only existing method at that time when we look at the 3D object detection problem on RGBD input. It takes an RGB image and its corresponding 3D point clouds as input. The first part of the network applies a 2D object detector on the image to get the 2D bounding box, and then extract features from the points within the frostum formed by the 2D bounding box. The next part of the network learns a mask to segment out the points from the 3D object. Finally, the last part of the network learns the bounding box parameters on the segmented 3D points. Despite its effectiveness, the Froston point net is a fully supervised method that requires large amounts of ground truth labels for 2D and 3D bounding boxes for training. However, it is very laborious and costly to get the strong labels of 3D bounding boxes on point clouds for full supervision. This is due to the amodality and incompleteness of 3D scenes represented by 3D point clouds. So one way to mitigate the challenges of getting large amounts of ground truth labels for full supervision is to do weak supervision. In the context of RGBD data, this means that the objective is to learn 3D object detectors given only the ground truth 2D bounding boxes during training. Unfortunately, this is very challenging due to the precision needed for bounding box size and orientation. Another possible way to reduce the amount of ground truth is the in-category semi-supervised learning. In this setting for RGBD data, we are given the ground truth 2D bounding boxes for all objects, but only few ground truth 3D bounding boxes for each object class during training. A third possible way to circumvent the requirement for large amounts of ground truth 3D bounding box labels is cross-category semi-supervised learning. And in this setting for RGBD data, we are given the ground truth 2D bounding boxes for all objects classes and the ground truth 3D bounding boxes only for a few object classes during training. We use strong classes to refer to the object classes with both 2D and 3D bounding boxes, ground truths. The object classes with ground truths for only the 2D bounding boxes are referred to as the weak classes. We deferred in-category semi-supervised learning to our second work on 3D point clouds and instead focus on cross-category semi-supervised learning in our first work for RGB-D data. The main reason is because there are already existing ground truths data for 3D bounding boxes on several object classes, and we want to transfer the knowledge from this existing data to new unlabeled classes to achieve good performances. Furthermore, we choose to work on RGBD data, and it requires 2D bounding boxes ground truths because it is significantly faster to train a person to manually label 2D bounding boxes for new classes than 3D bounding boxes as shown in this paper here. And our work on cross-category semi-supervised learning for 3D object detection on RGBD data was published in this paper at ICCV 19 by my student Siang Tang. Let us first denote weak classes with only ground truth 2D bounding boxes labels as C2D, and the strong classes with ground truth labels for both 2D and 3D bounding boxes as C3D. Note that the weak and strong classes are disjoint sets in the cross-category semi-supervised learning setting. Our proposed network consists of two parts. The first part is the Froston point net as our backbone network. We do full supervision on the strong classes with the same loss proposed in Froston point nets. The first loss is the instant segmentation loss to guide the network towards segmentation of the points in the frostum that belongs to the 3D object. The second loss is the 3D bounding box loss based on the anchor boxes. Since strong supervision is only possible with the strong classes, this means that the 3D object detection performance on the weak classes without ground truth 3D bounding boxes during training will be poor. Therefore, we propose a pre-trained box PC feed network to transfer the knowledge from the strong classes to the weak classes. More specifically, the inputs to our box PC feed network are the frostum point clouds features and the estimated 3D bounding box from the backbone frostum point nets. And the outputs are the box correction variable denoted as delta B hat, which serves as the correction to the estimated 3D bounding box B, and the box PC fit probability, which is the goodness of fit of the estimated 3D bounding box B. We pre-train the box PC fit network with randomly perturbed point clouds and ground truths 3D bounding boxes from the strong classes. More specifically, we emulate bad estimated 3D bounding boxes by large perturbation in P+, and good estimated 3D bounding boxes by small perturbations in P-. For training samples emulated with bad estimated 3D bounding boxes, we enforce a classification loss to output a low box PC fit probability and vice versa. Concurrently, we use a regression loss on the box correction value to give the correct 3D bounding box parameters. The pre-trained box PC fit network is then used to supervise the weak classes on the backbone frostum point nets. To this end, we introduce a fit probability loss to minimize the box PC fit probability of the estimated 3D bounding box by the backbone network from the weak classes. Note that the weights of the box PC fit network are kept frozen at this point, and hence minimizing the box PC fit probability is equivalent to improving the quality of 3D bounding box estimation from the backbone network. The final estimation of the 3D bounding boxes is taken as the sum of the initial 3D bounding box estimated from the backbone network and the box correction from the box PC fit network. We also add several regularization terms to prevent degenerate solution. In particular, we added a relaxed reprojection loss as a soft constraint to prevent large deviation of the projection of the estimated 3D bounding box from the ground truth to the bounding box on the RGB-D image. For example, the ground truth 2D bounding box is shown in green in this figure. We compute an upper bound and a lower bound shown by the bigger and the smaller blue boxes respectively. Our relaxed reprojection loss penalize the training when the projection of the estimated 3D bounding box shown by the yellow box over here falls beyond the upper and lower bounds. We further add the box prior losses to prevent volume collapse and large deviation of the scales of the estimated 3D bounding box. Here, we penalize the network when the volume and scale of the estimated 3D bounding boxes are too far off from the mean volume and mean scale per object class. We test our in-category semi-supervised learning framework from RGBD data on the benchmark indoor sun RGBD and outdoor KIDI datasets. Here's our experimental results on indoor sun RGBD compared with the existing fully supervised 3D object detection methods. Although our method does not have access to all the ground truth data during training, we still achieve a performance that is almost 80% of the best performing fully supervised Frosten point nets. We can also see that the performance of Frosten point nets drops significantly from 54 to 24.5 MAP in the semi-supervised setting. Here's several qualitative results from the indoor sun RGBD dataset. We can see that our semi-supervised method produces 3D bounding boxes that are close to the fully supervised Frosten point nets. Here's some more qualitative results from the indoor sun RGBD dataset. It's interesting to note that the object orientation estimated by our methods degrades in cluttered environments. This is probably due to the difficulty in guiding the network on the regression task of the bounding box orientation without strong supervision. We also show the results on outdoor KIDI datasets on the detection of cars, pedestrians, and cyclists. We also see that our semi-supervised method can achieve good performance compared to the fully supervised Frosten point nets on the outdoor KIDI dataset. One interesting thing to note is that our box PC net can also be used under a fully supervised setting to further improve the results on Frosten point nets as shown in the last line of this table. Here's several qualitative results of our method on the outdoor KIDI dataset. We can see that the quality of the 3D bounding boxes estimated with our semi-supervised method are comparable to the fully supervised Frosten point nets. Here's some more qualitative results of our method on the outdoor KIDI data. Similar to the indoor sun RGBD data, we can see that our method does not perform well on the orientation estimations in crowded scenes. So despite the good performance of our cross-category semi-supervised method, it still requires large amounts of 3D labels for the strong classes. Furthermore, this method also relies on 2D detectors and the availability of large amounts of ground truth 2D bounding box labels to train the 2D detector. So the obvious question here is that, can we do better? And the answer to this question leads us to the second work on in-category semi-supervised learning for 3D object detection using only 3D point clouds as the inputs. In-category semi-supervised learning means that we only use few labeled 3D bounding box ground truth labels per object class during training of our 3D object detector. Our work on in-category semi-supervised learning for 3D object detection on 3D point clouds, which we name it as SESS, was published in this paper at CVPR 2020 by my student Zhao. We adopt the mean teacher paradigm to achieve in-category semi-supervision with few labels per object class. We use the fully supervised VOTNet as our backbone network for the 3D object detection. We use 2 copies of VoteNet with the same architecture in our student and teacher branch respectively. Our SESS network takes the labeled and unlabeled 3D point clouds as the input. We first randomly subsampled from the mixture of these labeled and unlabeled point clouds to get two sets of point clouds. We then apply a random transformation on one of the randomly subsampled sets of point clouds before passing this transformed point cloud into the student network. The random transformation consists of a random flipping, denoted as fx, along the x-axis, and a random flipping along the y-axis, denoted by fy, as well as a random rotation around the upright axis and random scaling of the point clouds, denoted by R and S respectively. We flipped the x-axis of the point cloud when fx is equals to 1 over here. Fx here is determined by epsilon that is uniformly sampled from 0 to 1. So if epsilon is more than 0.5, we'll flip the axis, and if it is less than 0.5, then we'll let the axis remain. The flip along the y-axis is generated in the same way. When fy equals to 1, we'll flip the axis, and when fy equals to 0, we'll let the axis remain. Random rotation around the upright axis is given by uniformly sampling the rotation angle, denoted by omega over here, from a given range of angles from -v to +v. And we set this angle to -5 to +5 degrees for the ScanNet data set, and -30 degrees to +30 degrees for the Sun RGBD data set in our experiments. Random scaling of the point clouds is sampled uniform from a range of A and B, which we set to 0.85 to 1.15 in all our experiments. We concurrently input the other set of unperturbed point clouds into the teacher network. The random transformation applied to the input point cloud is also applied to the available ground truths. We use the supervised loss from VoteNet on the outputs of the student network with the perturbed ground truths. Learning from the unlabeled data is achieved by enforcing self-consistency between the outputs of the student and the teacher networks. Intuitively, self-consistency between the student and the teacher networks means that we are transferring the knowledge of the student network learned from the labeled data to the unlabeled data. Our consistency loss consists of three terms. First, the center-aware consistency loss that minimizes the alignment errors of the 3D bounding box center from the teacher and student networks. For each 3D bounding box from the teacher network, we consider the closest 3D bounding box from the student network to be its correspondence. Second, the class-aware consistency loss term that minimizes the KL divergence between the class probabilities from the student and the teacher network. This is to ensure that the object class probabilities of the 3D bounding boxes are consistent between the student and teacher network. Third, the size-aware consistency loss term that minimizes the mean square errors between the sizes of the 3D bounding boxes estimated by the student and teacher networks. Finally, we do a backpropagation with the losses to update the weights of the student network. We then update the weights of the teacher network as the exponential moving average of the weights from the student network. And here's the qualitative results of our SESS compared to the fully supervised VoteNet on the Sun RGBD and ScanNet datasets. We can see that our SESS consistently outperforms the VoteNet's overall ratio of labeled data on both datasets, denoted by the red segments over here in the bar chart. It's also interesting to note that our SESS already outperforms the fully supervised VoteNet at 50% labeled data for both data sets. Here's the qualitative results of SESS compared to VoteNet on the Sun Rgbd dataset. We can see that our SESS gives estimations closest to the ground truth at 30% labeled data. Our SESS is also able to detect more objects than the ground truth at 30% and 100% labeled data. Here's the qualitative results of SESS compared to VoteNet and the ScanNet dataset. We can see that our SESS gives results closer to the ground truth. In conclusion, I've presented our two works on semi-supervised learning to mitigate the requirement for large amounts of data for the important problem of 3D object detection. Our first work is on cross-category semi-supervised learning for RGBD input, and our second work is on in-category semi-supervised learning for 3D point cloud. Thank you.